Hello everyone, this is Ahmed Mahmoud. Today I'd like to present one of the hot topics in cryptography and security, which is security and Internet of Things. We'll start by introducing what's IoT, the current adopted architecture, the evolution of IoT attacks, our new proposed framework, and evaluation for our new proposed framework. So, what's IoT? Simply, IoT is an embedded device connected to the internet with some characteristic like it's power constrained, small in size, connected over wireless technology, have a relatively small memory, it's microcontroller or a tiny computer, often battery operated, and it can be a good friend or our worst enemy. Here is a generic IoT architecture. It's composed of three different layers. Perception layer, which is composed of the sensing devices itself, like sensors and actuators. Then the second layer is network layer, which is composed of routers, gateways, which is responsible for moving the reads and data from the perception layer to the application layer. Application layer, which is composed of cloud and server, and is responsible for mining, storing, analyzing the data. The attack to IoT has been through three different eras. The first era from 2005 to 2010, it was a new technology, there is no standard in place, minimum security measure implemented, it was easily hackable, and most of the threats was in a form of malware, virus impacting some Windows-based embedded control systems. In the second era, many manufacturers started to focus on this flourishing and opportunistic market, and with the number of IoT devices manufactured exploded to around 31 billion devices. However, the security of manufactured IoT systems was not an important consideration for those manufacturers. So IoT systems became a target for many attackers. The attackers started considering monetizing these attacks through crypto mining, ad click fraud, and spam email campaigns. Also, the politically motivated attackers jumped to the scene. Despite many companies started to address security of IoT, but still the level of protection is inconsistent, and many connected devices still have significant secure flaws. Starting this year, 2020, IoT devices are now in every area of our life. Also, the severity of attacks started to escalate more and more. Now, government and industrial groups began to enact legislation requiring higher level of security for IoT devices. Here are some of the security threats that IoT are exposed to. For example, in perception layer, it's exposed to node capture, malicious code injection, false data injection, replay, battery draining, sleep deprivation. Some of the security threats to network layers like distributed denial of service, spoofing, wormhole, man in the middle, amplification, routing information, and some of the threats to application layers like phishing, malicious worm or virus, malicious scripts, selective message forward. Now we'll talk about one of the infamous incidents of IoT related attacks, which is Mirai IoT botnet attack. But before moving ahead, please allow me to ask you a question. Have you ever purchased a device and forgot to reset the default username and password? If yes, please never do that again, and you will know why. Mirai started by continuously scanning the internet for IP addresses of IoT devices, and it just tried the default username and password. And surprisingly, it got access to hundreds of thousands of devices infected with Mirai malware. Then they became part of Mirai botnet that resulted in accessibility of several high-profile websites like GitHub, Twitter, Reddit, Netflix, Airbnb, and many others. The IoT devices that we have nowadays might still be used in the coming 10 to 15 years. So we are going to propose a framework to be secured. To address the vulnerabilities in the current architecture, we have recommendation in the hardware part and in the software part. Regarding the hardware part, we will adopt zero trust security strategy. In order to achieve that, we need to use TPM, which is a trusted platform module, and some of the related components. The TPM is composed of cryptographic coprocessor, random key generator, volatile memory, non-volatile memory. Also, it contains RSA key pair called endorsement key. That key is maintained inside a chip and cannot be accessed by any software. A platform can be considered a trusted platform if it has TPM and supporting architecture for the trusted building block. One of the key components in this system is PCR, which is Platform Configuration Register, which has integrity measurements stored in it at a particular index. If the value satisfies the requirement of the software or requesting entity, then it can ascertain the trustworthiness of the system. Otherwise, take an action. On the software side, we propose some amendment to the different layers. So for the perception layer, we propose using TLS protocol, which is Transport Layer Protocol, for a secure communication between devices and gateways. Also, we will make a use of a mix of asymmetric and symmetric encryption. For authentication and validation, we will use asymmetric encryption. And for the data transmission, we'll use symmetric session because it's less overhead. With the network layer, we recommend adopting fog computing, which distributes cloud computing capabilities and take it closer to the edge of the nodes, providing required computation faster, and this helps not only to avoid single point of failure, but also reduce bandwidth and latency issues. For the application layer, we recommended adopting MQTT protocol for data communication control and to leverage the use of role-based access control, RBAC. Here is the three-way handshake of the TLS protocol in the perception layer, and we can see that it's composed of two phases. The first phase for the initial connection between the IoT device and the gateway, and they are using public key encryption in order to ensure authentication for both sides. Then after securely exchanging a session key, it's just used for the ongoing communication. With this architecture, it's ensuring a higher availability and proper authorization for all the different users. So for instance, when Alice is trying to connect, her, her role as a programmer is fetched from the roles entity, then the associated permission is fetched from the permission entity. For the data communication control, we would like to introduce MQTT protocol, which is a protocol that provides publish and subscribe messaging. And it was specifically designed for resource constrained devices and low bandwidth, high latency networks such as dial-up and satellite link. It seems to be a good fit for IoT. With MQTT, we have publisher, subscriber, and the broker. The publisher are simply like the sensors or the devices for publishing the data. Subscribers are the other client that would like to receive this data. The broker is the one orchestrating these operations. We can see from the model here that there is no direct interaction between the publisher and subscriber. Simply, the publisher sends a message to the broker, then the broker acknowledges back to the publisher, the broker sends a message to the subscriber, and subscriber acknowledges back. Some of the advantages of MQTT protocol are like its efficient data transmission, low network usage due to minimized data packets, efficient distribution of data, successful implementation of remote sensing and control, fast and efficient message delivery, usage of a small amount of power, reduction of network bandwidth. Finally, we have conducted a quick evaluation between the standard IoT architecture and our proposed architecture, and we have witnessed improved confidentiality, integrity, and privacy. Thank you.